Record. Okay, so welcome guys to the design of a level 2 high power rocket workshop. This is going to be part 1, which I'm primarily going to focus on deployment, recovery, and avionics. Second one is going to be a lot more about like the structural stuff and construction. Yeah. Starting off. So first, I just want to go over deployment things and single deploy versus dual deploy. I know you guys are probably already familiar with single deploy versus dual deploy, but it's important to understand the main difference being that single deploy only uses only one parachute, which simplifies your design quite a bit, but if you're going up higher, that can lead to a lot more drift in the wind. Using dual deploy, that then necessitates adding more features to your rocket, typically eBay and an altimeter, oftentimes multiple parachute like sections, although that depends on your design, but it significantly reduces drift by using a smaller drag parachute, so that your rocket isn't in free fall but is still falling relatively fast before deploying a main chute close to the ground. So you save a lot of time on that. And just to give you some an idea, I have I'm sure you guys are familiar with the open rocket simulation graphs. I have a single deploy simulation versus a dual deploy simulation. You'll notice the main difference between the two is the recovery device deployment event. In the second one, that's around 137 seconds or so, where it significantly slows down to reasonable velocity. The important thing, though, that I want to talk about is which one you should actually be using. I think it's important to, like, there's no set right answer for any of this stuff. Maybe there's for some of it. But when you're designing your rocket, you need to look at where you're planning to launch it, what the rocket is like, how high it's flying, and other sorts of characteristics. Are there any limitations on your field? Are you going to fly at CMAS and you have to avoid that massive power line that's in the middle of it? But in general, the higher you fly, the harder it will be to design a safe single deploy rocket. In the case that like you're in the Mojave and you're able to drive like 10 miles to pick up a like single deploy rocket that like drifted far away after you launch it to like 5K feet, then like, yeah, you could. It's probably not a great idea, but you could. Yeah. I think my personal recommendation, I think when you're doing an L2, it is a great opportunity to learn dual deploy. So I think that it's probably a good idea, although you don't have to. Generally on the, it definitely is an unreasonable option to do single deploy if you're flying on a smaller L2 motor. And next up, ejection methods. So on the right, you can see a picture of an E-match, typically used to actually light off black powder charges. And that is going to be the most reliable method for deployment, because using a black powder charge, you can test it, or you can do calculations to figure out how large of a charge you need beforehand, and then ground test it so you can guarantee that it will work in flight. And for those, you need some kind of altimeter to deploy it. There's also motor ejection, which is probably more common on smaller motors. Basically, after your rocket motor burns out, there'll be a short delay before it fires its own, basically just a black powder charge at the bottom of the rocket off. In general, it's a pretty good way to do separation events. The issue is, I mentioned black powder charges are easy to test, calculate. You can't really test the motor ejection on the ground because that would involve lighting a motor off, which unless you, for some reason, built like a setup for it, you really shouldn't do. It does work good as a redundant ejection mode though, and so there's always the option to do that. It is important to note if your rocket motor has an ejection like delay of like plugged seconds, that means there's no ejection on it. I know that's something that has confused a lot of people. I think, yeah. And finally, we've never used it in AIAA anywhere, but there's also CO2 ejection, which is functionally similar to black powder ejection, but there's no fire or ejection, or hot ejection gases, I should say. So it tends to be safer. Although the reason we've never used it is because it's significantly more expensive. So it's something to know about. If you really want to, you can look into it, but it's not super necessary. Wait, oh yeah, okay. I thought I was missing something. Next, I kind of want to move into recovery, and I don't know the statistics off the top of my head, but I believe recovery failures are responsible for a majority of rocket failures, according to a survey the NAR did several years ago, I think. And so it's very important that your recovery devices are deploying on time, that you're using appropriately sized parachutes and the like, and that your rocket is actually able to get them out of the rocket. The first thing, just sizing. This is another thing where there's no set, like, use a 36-inch parachute because it's the parachute size. It depends. First off, referring back to slide 4, you want to figure out how much drift is acceptable. Whether you can drift, a mile, that'd be a lot, or maybe only like a few hundred feet. You really have to keep that in mind when you're doing simulations. There's also, in general, the smaller your parachute, the stronger your rocket has to be structurally to compensate for it. But then also the smaller your parachute, the lower your time of flight and the lower your drift. So ideally you want to find a nice medium where you're descending quickly, but not quickly enough that you're going to break things. And to give you kind of an example of the range, I know my L2 rocket, according to the simulation, descends at approximately 27 feet per second under drogue. The USLI rocket this year descends at 77, which is significantly faster, but it's important to remember that the USLI rocket, we had aluminum bulkheads, carbon fiber fins, blue tube construction, and all that's a lot more sturdier than my rocket's made out of like thick cardboard for the airframe, and I have like wood fins. So you really have to keep in mind the limitations of the materials you're using, and what they can actually withstand. Continuing on, parachute rigging. Unless you're using CO2, you need to make sure that your parachutes and shock cord are actually protected from ejection gases. This is typically done through Nomex blankets, sheaths, no mix blankets and sheaths. The AIAA has a bunch of them, but basically just fire-resistant cloth. Copious amounts of dog barf also work. I know way back in the L1 workshop, I mentioned this about buying rocketry supplies. This is another good example. Dog barf, as it is usually sold by rocketry vendors, is just cellulose insulation, and you can buy basically a lifetime supply for like $12 at Home Depot. It's definitely more than you will ever need, but in case you want to buy it cheaper. Another really important thing, use metal hardpoints like U-bolts or I-bolts to secure your recovery rigging. It's important that things aren't being ripped off. And that kind of goes hand in hand with making sure bulkheads are actually able to withstand the recovery forces. It's always a good idea to double check using some FEA, if you know that, or just plain structures math from whatever your last structures course was. Is a very practical application. Yeah, I know this was a mistake that we made the first year we competed in USLI because we only used 1/4 inch wood for the bulkhead, for the bulkheads on our rocket, and that ended up leading to one of the bulkheads getting completely ripped out. 1/4 inch wood can work well on, you know, smaller L2 rockets like the rocket I have. I think I want to say I have 1/4 inch bulkheads, and that works fine because it's smaller. But when you go up on the larger scale, you need something thicker, sturdier. But the same would also go if I wanted my rocket to descend much faster, I would need something stronger than 1/4 inch. Yeah. Next thing, you need a lot more shock cord than you think you do. Typically, you want like something like 2 to 3 times the length of your rocket in tubular nylon. And this is all to make sure that your rocket doesn't, like, the segments of your rocket aren't colliding in midair. And obviously this depends on your configuration. For some things you might need more, for some things you might need less. And so to give you an example of parachute placement, you can see on the right a picture of our full-scale launch from this year. And I just want you to notice the lengths of the shock cord. And I know this is after deployment. So, you know, there's no upper airframe on there. But you'll notice if the lower airframe were to swing down, if the upper airframe were there, it wouldn't hit it because of where the parachutes are placed and how long the shock cord is. I'm going to, so that being something important, would you guys like if I just took a short break to go and kind of draw out an example?
Sounds good.
Okay.
Sure.
I'll take a quick moment to, got my drawing tablet and everything. I'm prepared. Okay. So use paint. Okay. So when you're actually making a rocket, okay. So I have the lower airframe, my fins on it. And as I said, the important thing is that when your rocket parts are all dangling on the shock cord, you need to be sure that they aren't going to hit each other. So our shock cord coming out. We have our parachute, over here, and it connects there. But the thing is, we then need to discern how much extra space we need below, like beyond that, to actually secure the upper airframe. And so you'll typically want, at least a good buffer here, maybe do like at least 2 or 3 feet before you have your upper airframe. Very nice drawing. Which can then connect to the parachute hardpoint. So you'll notice this, the length of this segment is roughly roughly 2 times the length of the segment that connects to the upper airframe. And this is kind of where you get the 2 to 3 times your body length, because when you look at it, this is roughly equal to the body length of your lower airframe right there. So yeah, it's important that it's a really easy mistake to avoid, but one that's important. And also the same goes for when you're placing your lower parachute, because obviously you need to keep those separate. Okay, so back to the slideshow. Going to continue on, and now we get to my favorite part, avionics. I'm going to be primarily talking about altimeters here. It's important to know the word altimeter is a little more broad than what I'm using here. I'm going to specifically refer to dual deploy altimeters. Altimeter can also refer to just stuff like Jolly Logic makes some like little small USB stick size things that just record altitude, and that's not particularly useful for us. The kinds of altimeters we use are ones that can detect flight events, such as apogee, launch, etc., and then actuate charges based on that. And pictured is a RRC3, a MissileWorks altimeter. We've never owned one, but I know it's pretty popular, and I've seen some other teams at NASA use it. I personally prefer the term flight computer since I think that's a little more accurate, but dual deploy altimeter is generally more widely used. And here we can quickly see the 2 types of altimeters owned by the AIAA, that being the Stratologger CF and the Raven 4. And I think they do kind of a good job of illustrating some of the differences you'll see in altimeters. I guess one thing I'm going to say is I don't think I'm going to go too much into like specifically using altimeter. When you're using altimeter, you should really read the user manual, because that's the best way to learn how to do it. All altimeters are slightly different. They'll all make different beeps that mean different things. You program with them with different programs. But in general, they're not too hard to learn how to use. But to give you more of an idea of the different types of altimeters, the Stratologger, I think is somewhere in the range of $60-ish, and uses only a barometer to detect your apogee and the current altitude for logging. And it does logging at a relatively low frequency. It's very simple to set up, and there's very few ways you can do it wrong. Actually, maybe not by comparison. And additionally, you have some nice things like the data port, which let you just connect it to a computer with another cord, and such. On the other hand, you have the Raven 4, which is more complex to use. I know it's not. I'm realizing this now that I have the Raven 4 on it's much larger in the picture, but the Raven 4 I believe is smaller and is really tightly packed, and just has a lot more features, but it's also a lot more expensive. And so it does things like log a lot of data much faster. I know the Raven also has an accelerometer. And the key difference, accelerometer measures the acceleration. So rather than just measuring pressure and indirectly altitude, using the accelerometer, the Raven can get a better idea of the velocity of the rocket, which helps with detecting apogee and whatnot, and also helps when you're actually flying at transonic speeds, since when you get to transonic speeds, I don't know if how many of you have already taken aerodynamics, but there's a lot of weird stuff that goes on with the pressure. Pressure drops once you like break the sound barrier, and if you're pretty much all altimeters account for this, but if you're using altimeter that didn't have any sort of code to account for that pressure drop, then it might think that that was apogee and deploy while you're breaking the sound barrier, which is obviously not great. And so, yeah, having accelerometer is a nice feature. The other downside to the Raven being it's more complicated to use. One of the fun stories that we have from our first, I want to say this was our PDR that we presented to NASA. When we told them we were using a Raven 4, they were kind of concerned and told us a story about how there was a team that accidentally misconfigured their a Raven 4 altimeter, and the rocket on its way up deployed at 800 feet while the motor was still lit, and that pretty much destroyed the whole thing. Yeah. Moving on, in case you guys are looking, if you ever want to get your own altimeter or want to look at what else is available, I think one of the more interesting series I've recently found, if you go on eggtimerrocketry.com, they sell some like really cheap kits for altimeters. I don't really know how they get them that cheap. I guess that's probably because they're not paying anyone to assemble them. But I know they sell like a dual deploy altimeter for like $35. I think there's a $25 one too. And I also found a neat comparison table of a whole bunch of different rocketry altimeters that I think I originally found rocketry forums. But I think also, even if you're not thinking of getting one for yourself, it can be interesting to see what kinds of altimeters exist and what features are common in other ones. I know if you go all the way up to the much higher end of altimeters, you can get to stuff that has like real-time telemetry built in, GPS trackers built in, other such things. I know, I'm not sure you can really buy Joe Barnard's like thrust vector thing now. I think that's been out of stock for ages. But the other thing I have in the picture is a Jolly Logic shoot release, which you guys probably all remember from our rocket this year. And just to summarize it real quickly, essentially it's a altimeter that just deploys and unhooks a rubber band around your parachute at a set altitude, so that you can essentially turn a single deploy rocket into a dual deploy rocket. And it is kind of a weird gray area of built like a single deploy rocket, but it's flying dual deploy like flight mode. And yeah, they are kind of aggressively expensive. But continuing on using Altimeter, as I said before, please read the manual. You want to know how it actually works before you use it. The other thing, double, triple check your configuration before you actually close up your rocket. That will save you from being that USLI team that blew up at 800 feet. It's also important that you drill, because essentially every altimeter relies on a barometer in some form or another. You need to drill a pressure hole, essentially just a hole that opens up the interior of your eBay to outside so that your barometer can actually read external pressure. And finally, this is one that I think a lot of people kind of skip over, is actually isolating your eBay from ejection gases. In any case, in this photo, you can see it, and it's not really a render, but a screenshot from CAD of the original USLI rocket. And you can see the sleds that are kind of in the middle that are bolted to either end. Those flat surfaces provide a mounting point for all the, the altimeters and, whatever batteries you need. And I think in general, this kind of design of an eBay using just like a sled that goes on threaded rails is probably the simplest way to design eBay, and I think probably, in my experience, the most common. It's a pretty easy way for when you're building your rocket to do one. If you want to get fancy and do something like this year's rocket with the like twist to install, you totally can, but that's a lot more effort. I know one of the mistakes that we did make on that first year's rocket was we didn't do anything to isolate from ejection gases. And I should clarify, the reason you need to isolate from ejection gases, even if you're using CO2, which, obviously with the black powder ejection gases, they're hot and can possibly melt wiring and damage stuff. But even if you're not using them, just the gases leaking into the eBay can increase the pressure inside the eBay. And then because of the reliance on a barometer, that changes what altitude the altimeter thinks it's at. And so in a worst case scenario, that can lead to your rocket thinking that it's actually like 500 feet off the ground and it needs to deploy another set of parachutes. And that's not necessarily a catastrophic error, deploying extra parachutes, but as I mentioned before, that could lead to a lot more drift than you had planned on, possibly leading you to power lines and highways and other such stuff. Yeah. Continue on. There's some other avionics systems that I want to mention briefly. I don't think that these are all that important for building your own L2, but they're good to know about nonetheless. Telemetry systems, just for getting real-time telemetry, kind of similar to how Mission Control does it at any space launch, actively streaming data from the vehicle. You'll need some kind of ground station with an antenna for this. And typically, I think in most cases, this will just be combined with an altimeter. I don't think this tends to be particularly important in high power rocketry. It's more experimental rocketry that this is useful, but it's a really cool feature nonetheless. And the other type of system I wanted to mention was GPS trackers, which can actually be pretty helpful if your rocket is flying particularly high and you need to track it down. For GPS trackers, I know it's pretty common to use like handheld antenna trackers to track them. But yeah, and those can also be combined. There are some altimeters that come with like onboard GPS tracking, but there's also other just standalone GPS tracking boards. And finally, I can give you guys a moment to ask questions before I'm going to tab out to some other programs to give you some examples and show you some such stuff, different altimeters. Any questions before we continue?
I'm all good.
Okay. In that case, I'm going to move this. I'm going to quit out. And first off, I want to show you this. This is a program called Perfect Flight Data Cap, which is the desktop program that you use to interface with a stratologger. And I mean, I do have a stratologger on me right now, but I don't have the data cable, so I can't actually plug it in. So this is the log from the full-scale primary altimeter this year. And we can look at it just to kind of see what's going on. And you can see, obviously, this very closely matches the actual the simulation from what you'd expect to see of a dual deploy rocket. So, you have the acceleration as the motor burns. Motor burnout is somewhere in this region. That's not something detected by the stratologger, although I believe that there's other altimeters that can detect motor burnout. And then you get all the way up to apogee, and where it deploys the drogue parachute marked by this D. And you can see there's kind of a sudden drop in altitude. And it's possible that this might be due to something like there was a small leak causing some ejection gases to get in. Or sometimes you do just get jolts due to the like sudden accelerations. But yeah, the important thing is that these jolts aren't taking it all the way down to main deploy altitude, because that's where things go wrong. The other thing down here, you can see the M indicates where the main parachute was deployed. Right around, I think this is 700-ish feet. And you'll notice it doesn't actually start slowing down until around 500 feet. And that's because in an open rocket, in simulation, parachutes are just treated to deploy instantly, which in reality isn't realistic. As soon as you have a charge go off, you aren't immediately going to start decelerating. So there is some time in which the parachute is unraveling. And yeah, for that reason, it's important that your main deployment altitude is reasonably high. 700, 800 feet tends to always be good. You can go lower. You just need to make sure that your parachute will deploy in time. When in doubt, you can always do a drop test and time how long it takes your parachute to fully deploy. But yeah, in general, these applications, each altimeter will have its own desktop application typically. There's some altimeters out there that even use like apps. I think the hot thing right now is Wi-Fi or Bluetooth altimeters that you like configure with your phone. so that you don't have to like, take your rocket apart to like configure the altimeter. But that's what all the cool kids are using these days. Yeah. Moving on to OpenRocket. This is the level 1 thing. I'm just going to close this. Here we go. So this is my L2 rocket, and I want to show you a bit of stuff about the simulation. So you guys probably, I remember doing simulation stuff in the L1 workshop, and we kind of focused mostly on this graph right here, which is probably the most important graph you'll get from the simulation, which is your altitude over time and your vertical velocity. And you're able to see when recovery events occur, etc. But it's also good to know the other types of plots that OpenRocket can create. And you can pretty much graph anything you want against any other thing that you want. Like if I really want to, I could like graph Mach number versus like yaw moment coefficient, but that's probably not very useful. Typically, it's good to use these plot presets. And so you can see vertical motion versus time is what we were just looking at. And that graph is just your motion in the z direction, up and down altitude. But you also have this total motion, which accounts for your other directions in flight. Another really useful thing that I want to make a point in showing was the flight side profile. And you remember earlier I was talking all about simulate your drift, like actually know where your rocket's going. This is a good way to do that. And this graph is pretty easy to interpret. It is literally just a side view of what your rocket will look like. And so you can see the different events are also marked on here. So you can see motor ignition, motor burnout, all the way up to the drogue deployment, and then drifting down and over. And you can see, according to this simulation, with the given like wind parameters that I set, it should land like about 950 feet west of the launch site. So you can see there's position east that's negative, position west. And if I go back and change things about the simulation, using edit simulation, if I bump up the wind speed to like 14 miles per hour, and I run it again, you'll see all of a sudden now it's drifting a lot farther. And so it's a good idea to go and simulate. But before you actually go to a launch site, go figure out how far you can reasonably drift at that launch site, and then try to simulate and find the maximum safe wind speed you can launch in. And that's something useful you can use to prevent yourself from flying into a tree. Yeah. Moving on, just to show a couple of the other ones, you also have stability versus time. I know the annoying thing is it likes to graph the entire flight, even though you only care about like the first little bit. Yeah, so the red right here is stability. You can see stability increases during flight typically because your motor is losing mass, so your center of mass is moving up, increasing stability. I'm realizing this rocket might need a little bit of redesign. That stability looks kind of low before 1 second. So you can see all the way down here, it's at 0.1 stability. That seems wrong. Okay, I can fix this later. But yeah, it's important to note this is the average stability this number Open Rocket gives you. You always need to make sure that you're always above 1, even at takeoff. And there's a good amount of other ones that I encourage you to explore and try and interpret for yourself. But yeah. In any case, some of the other things just to highlight real quick before I finish up. One of the things that you will need is, if you're doing dual deploy, some kind of eBay, which is generally pretty easy to model with just a coupler, 2 bulkheads, and a mass object. One thing that I didn't specify earlier is if you use this mass component in Open Rocket, you're able to specify what type of mass it is. And so this is just specified as an altimeter. And you can add the mass of the board and like the battery you need to power it. Yeah, that doesn't really do anything simulation wise, but it can make your model easier to look at and interpret. The other thing, dang, there was one thing I wanted to mention that I'm forgetting. Oh, I'll remember it later. Okay. I guess in that case, I think that kind of concludes all the stuff I wanted to cover today. If there's any questions that you have, or I know I was forgetting. I want to new window show you guys some of the other altimeters. So just go on to Apogee. Sorry, I probably should have had this window open beforehand. It's my fault. Apogee has a section that's just for dual deploy altimeters. So you can see like other things like the Easy Mini, which is similar to the Stratologger. The thing I wanted to show you guys was kind of the upper end of altimeters, which I don't, in most cases, you don't need something like this, but something like the Telemega, which is $461, has onboard GPS tracking. I think you need a ham radio license to even use this. It's quite the altimeter. You can see it has all kinds of channels and is super configurable. Yeah, to give you an idea of the upper end. And finally, I guess there's one thing that I didn't mention being timers. You can buy timer boards, which essentially is like an altimeter in that it will detect your launch, and then rather than firing something in Apogee, it just fires a charge or whatever's connected to its terminals at a set time, and that's typically used for lighting a second stage motor, which I think in general I'd probably discourage you from trying to do a staged rocket as your L2 cert, but yeah. Yeah. Okay. Anyways, that's the actual end, I promise now. Other questions, comments, concerns? Cool.
Good job, Max.
Thank you. Okay, I'm going to
Thank you,
stop
Max.
recording now.